In this video, we're going to talk about volume of solids of revolution and finding that volume using what's called the disk method. Now, you've already examined the disk method a little bit when we talked about the wedding bells and when we talked about, the volume of a sphere and how we calculated that. So if we have a region such as this one, and we were to rotate that region about the x-axis, then that region would come down here at 180 degrees. It would be something like this, and then you can think about it would form circles as we rotate it all the way around, but that would form a complete solid. There would be no hole in the middle. And so if you think about slicing that at any particular spot, you can think of it as a stack of circles, but they're discs. They have a little tiny bit of thickness and they're discs, but of course the more disc you make, the more you slice it, the thinner and thinner it gets till it's so thin it's almost just a circle. And so you can almost call this the circle method, because when you get infinitely small delta x, it's almost like you just have a circle. And so the volume of solid with a disk method, it looks like this. We're going to have this region, okay, given a region A with area of cross sections A of x, and the volume of the solid of revolution would be, well, just this solid in general would be the A to B, which would be the beginning and ending of the region from x, the area dx. Now, since we're dealing with our disk method, for our disk method in particular, this is a general rule here, but for our disk method in particular, we're going to use the area of a circle. So our area, of course, of a circle is going to be pi r squared, pi times the radius squared. We're going to bring the pi out, and we're going to put r squared, and we're still going to leave dx because our variables will be in terms of x, or we could have c to d or a to b, it doesn't really matter, and then r squared and dy. Sometimes if we're rotating around a vertical axis, we will use will be a dy problem instead of a dx problem. And so important points here: if the region's rotated around the x-axis, which equation is y equals 0, is the equation of the x-axis. Another horizontal line would be y equals some other number. Variables must be in terms of x, so you'd see y equals. Now if you're rotating around the y-axis, so that the equation of that is x equals 0, or another vertical line, x equals some number, variables must be in terms of y. So you have to solve the equations for x if you're going to do that. We're rotating around a vertical axis. Okay. Let's look at an example. Find the volume of the solid created by rotating the function f of x equals the square root of x on 0, 1, the interval 0, 1, about the x-axis. So we're going to draw and sketch a picture, because for a while at least it will be helpful for us to sketch a picture. We know what the square root function looks like. It hits the origin and it comes up like this. It looks like a parabola on its side, half a parabola on its side, and that's really what it is. It's a piece of a parabola. The equation really could also be written as x equals y squared. That would be another way of writing it. So if we're going from here, which is 0, of course, over here we'll say this is 1, then the region that we're rotating is this region here, is the region that we're rotating. And so if we come out here and we draw the other side of that, and we realize that, hey, it would be curved around like this, it almost looks like a cup, a little, one of those fancy stem glasses that you could drink out of. Okay. Now, so our area, or our volume, is going to be from 0 to 1, and don't forget the pi, and then the radius squared. The radius is from here to here. At any point, this is my radius. Well, that equals the square root of x. This is, if this from here is this distance here is x. This distance is f of x, which of course is the square root of x. So that's our radius. So it's the square root of x squared dx. And we simplify that, that would be from 0 to 1. Square root of x squared is just x dx. Now we can do this by hand. We don't need our calculator for this one. And we would take pi, and then we would take the antiderivative, which would be x squared over 2, evaluated from 0 to 1. And so I plug 1 in. 1 squared would be 1 over 2 minus, and of course if I plug 0 in, I'm just going to get 0. So that would equal 1/2 pi, or pi over 2, whichever you prefer. And that would be our volume, and you could put units cubed on there since we don't know what the units are. We just say units cubed. That would be our volume. Okay. Find the volume of a solid obtained by rotating the function, the region, y equals x cubed, y equals 8, and x equals 3 about the y-axis. So now we're rotating about the y-axis. So let's look at what that looks like. We're going to sketch that. Y equals x cubed. We know it comes up, goes through the origin, it comes up like this. Looks like half a parabola again, but part of it's, the other part of the parabola seems to be flipped over. Now it says y equals 8, which is up here. And it says x equals, it should say x equals 0. That's a mistake there. It should say x equals 0, because this is the region that we want to rotate right there. And we're rotating it about the y-axis. So our other half is going to come out here. And then it would have that same basic fancy glass shape, like a stemware, like stem glass. It would look like that, or half an hourglass if you want. That would be the shape of our solid. And but we need to, in terms of x, we need to solve these equations for x, because our radius is going to go from here to here, and so that's x. So we need an equation for x. We can't just say x, we have to have an equation. So we take that y equals x cubed and we solve it for x, and x is the cube root of y. And so we're still doing it the same way. Our integral, our pi, and then the cube root of y is going to be our radius squared dy. It's a dy problem because we're rotating about a vertical axis. And it goes from 0 to y equals 8 because we're dealing with y. So from 0 to 8. Okay. And you could do this one by hand if you wanted to. It would be a little more timely. Take a little more time, but it would be y to the 2/3 power dy. Okay. And so if I take the antiderivative of that, would be y to the 5/3 power times 3/5, evaluated from 0 to 8. Of course, good thing is plugging in 0 is going to give us 0 again. So it'd be pi times, now I'm going to put the 3/5 out here, 3/5 pi times y, which is, we're going to plug in 8 for y. Eight to the 5/3 power, which is 3/5 pi times 8 to the 1/3 to the 5th power. 8 to the 1/3 is 2. The cube root of 8 is 2, and 2 to the 5th power is 32. So this turns out to be 32 times 3 is 96 over 5 pi, and then it's minus, this is all minus 0, because you know when you plug in 0 you're going to get 0. That is the disk method. Okay. Now sometimes we're going to have to use what's called the washer method, and we know what a washer looks like. We're going to have a washer has an opening in the center, and so if you have something such as a cylinder that is open in the middle, that would be a washer method. And I'll show you, we'll do one that comes up here in a minute. But now you're going to have, and when you have a region, you're going to have this would be, right here would be the inner radius. And we're going to call that little r. And then here, from here to here, that would be the outer radius, which we're going to denote with capital R. And so essentially we take the area of the larger circle, we take that and figure out that volume, and then we would subtract the volume of the smaller one, which is coming out. So if you wanted to do it with a disk, if you wanted to do the outside with a disk method, it would be the integral from a to b, so it'll be pi, of r squared, okay, and we're going to leave dx in there even though we know that's not quite right, minus the pi times the integral from a to b, same thing, of little r squared. Well, we can put that all into one integral, and it'd be pi times the integral from a to b of capital R squared minus little r squared. And as I said, we're going to leave dx in there for now, even though it might be dy. Okay, we just like to remember that it's there. And that is our formula we want to remember for the washer method. We have an outer radius and inner radius, and we want to remember that. Okay, so find the volume of a solid of rotation when the region bounded by y equals x and y equals x squared is rotated about the x-axis. Okay, so let's draw a picture again. Y equals x, we know, goes through the origin and cuts the first and third quadrants in half. Y equals x squared, we know it goes down, touches the origin, and comes back up here. And so you see that this is the region that we want to rotate right here. And we know it starts then at 0 and it ends at where they intersect a second time, so where x equals x squared. There's two spots where that happens. Obviously 0 equals 0 squared, but also 1 equals 1 squared. So it's from 1 to 1. And we're rotating about the x-axis. So as you can see, the region here, the region touches the x-axis, but the rest of the space, there's this gap. Anytime that there's a gap, we're going to have some kind of hole or indentation in the solid when we rotate it around. If we created the 180-degree rotation here, it would look like something like this. Would this be here, and then it would go around to here and around to here, and so you can see how that would kind of look like a tornado, almost like a tornado there. That's solid, but you'd have an inside, like the eye of the storm there. Okay. So we have to figure out our inner radius and our outer radius. So my inner radius would go from here. This is where I'm rotating, so it would go from here to here. And then my outer radius would go from here all the way to here. So you can see that it goes from the x-axis to the y equals x line is the outer radius. So r is going to equal let's do that in black, x. That is our outer radius. This distance is y equals x, so that's just x. Then our little radius is going to equal this distance, which is our x squared. So the top function here, if we're thinking about the area of the function, it would be the top function is x and the bottom function is x squared if we were calculating the area of that region. So then we have our capital R and a little r. It'd be pi times the integral from 0 to 1 again, and it'd be x squared minus x squared dx. And again, we can do that one by hand taking the antiderivative of x squared, which is x cubed divided by 3, minus the antiderivative of x to the fourth, which is x to the fifth, divided by 5, evaluated from 0 to 1. And so obviously, again, if we put 0 in there, we're just going to get 0. So if we put 1 in, we're going to get 1/3 minus 1/5 minus 0, and that would be, okay, you could leave it that way and that would be fine. You would be welcome to leave it that way, that would be okay. I'm going to complete it to getting something at least one step further. 1/3 minus 1/5 would be 5/15 minus 3/15, which is 2/15 pi. But again, on the AP test with a non-calculator, that would be an acceptable answer right there. Okay. In our next video, we'll look at some more examples of using the disk method and the washer method.